Chapter 5, Section 2. We want to further investigate this idea of accumulated change and eventually get to what is called the definite integral. So let's start with some basic terminology. We looked at these graphs and we estimated this area under the curve using these rectangles by tables, and so we need to add some terminology so that we can calculate these when we don't necessarily have a graph, but we do have a function. So the leftmost endpoint where we start will be called A. B will be the rightmost endpoint, N will be the number of rectangles that you are using, and delta T is going to be the width of each of these rectangles. There's also a special relationship between all of these variables, where delta T, the width of each rectangle, is going to be equal to B minus A divided by N. So looking at this graph in front of us, we have that A equals 0, because we're starting at the point x equals 0, B equals 10, because we see it goes as far as 10, N equals 5, you can count the number of rectangles we used underneath the curve, and there's 5, and delta T is going to be 2, because that's the width of each rectangle. So let's look at an example with a function and see how we can find left-hand estimates and right-hand estimates when you're given a function. So if T is given in years over a 5-year time period, a population increases at a rate given by f of t equals 6 plus 0.3 t squared. Find the overestimate and underestimate of this population if delta t equals 1. So here, A will be 0 and B will be 5 because we're looking over 5 years. So we're starting at time 0 and ending at time 5. Since delta t equals 1, we're going to be counting by ones. So we'll look at A equals 0, A equals 1, A equals 2, 3, 4, all the way up to 5, which is B, our endpoint. And since delta t equals B minus A over N, we can solve for N, and we know that we're dealing with 5 rectangles. So how do we find a left-hand estimate and a right-hand estimate? Well, again, to do these, we're doing a rate times a time. The time we know is 1. That's delta t is going to give us the time periods we're looking at every year. To find our rate that we're multiplying by, we need to take each of our endpoints starting on the left and plug them into the formula. So we're starting at 0 because that's our leftmost endpoint. So we want to first take 0 and plug it into the function. If you plug 0 in, you're going to get 6. So you do 6 times delta t, which is 1, plus, then you're going to increment over from 0, delta t. So we increment over to 1 because that's our delta t. You then take 1 and you plug it into your formula. When you plug in 1, you get 6.3. You do that times delta t. Plus, increment by 1 again, you get 2. You plug that into a formula, you get 7.2 times delta t. Plus, increment by 1, and then you get 3. You plug 3 into the formula, you get 8.7 times delta t. Plus, then you increment by another 1, you get 4. You plug 4 into the formula, you get 10.8 times delta t, which is 1. When you do a left-hand estimate, you do not use the rightmost endpoint. So you would stop at 4, because if you were to increment another one, you would get 5, and that is the rightmost endpoint. So you stop at 4. When you add all of these up, you're going to get 39. We also want to look at a right-hand estimate. Again, when you do a right-hand estimate, you start on the right and you work your way backwards. So we start with the rightmost endpoint, which is 5. You plug that into your function to get your rate, and you'll get 13.5 times delta t, which is 1. Then you increment down by delta t, so the next one down is 4. You plug in 4 into your function, you get 10.8 times delta t, which is 1. Then you plug in 3, which is 8.7 times 1. Then you plug in 2, you get 2.7 times 1. And then lastly, you're going to look at the last one as 1. And the reason you look at it as 1 is because we don't use the leftmost endpoint. So again, like the other one, we didn't use 5. This one we won't use 0. So the last one we'll look at is 6.3 times 1. You add those all up, and you're going to get 46.5. So the bigger number is going to be your overestimate, and the smaller number is going to be your underestimate. So again, you'll just be plugging numbers into the function given. So what happens when n gets larger and delta t gets smaller? The more rectangles you put in, the better your approximation will be. This is the same thing as making delta t smaller, and that'll give us a more accurate approximation. So sometimes you'll be calculating things with n equal to 5, and then maybe n equal to 10, and then maybe n equal to 20, because what's happening is you're getting a more accurate approximation. So in general, the left-hand estimation is the sum of the areas of each of the rectangles. If we label each of the points we use, where our starting point is A and our ending point is B, with a subscript of t, so t naught, t sub 1, t sub 2, labeling each point, then each rectangle is going to have an area of f of t sub 0, so that's the y value representing the height, times delta t, which is the width. That's the area of any one rectangle. And we can do this for each and every t sub number that we would use for a left-hand estimate and a right-hand estimate. With a left-hand estimate, we don't use the last one, which is b, which we represent by t sub n. So our left-hand estimate, the last y value is f of t sub n minus 1 times delta t. And for a right-hand estimate, we don't use the leftmost point. So instead of starting at f of t sub 0, we start at f of t sub 1, and we go all the way out to f of t sub n. So this is just a general way to write it. And in math, a lot of times we don't want to write it out with lots of addition, of adding up all these rectangles. So we have summation symbols that represent the same thing. So we can write it as you see on the bottom, with a summation symbol telling you how to add up each of these terms. Well, eventually, we want the right-hand sum to equal the left-hand sum, because that means that the overestimate has come down, the underestimate has come up, and now we've hit the exact area under the curve. So what that means is we're letting n get bigger and bigger and bigger until this happens. We're putting in more and more rectangles. So what we're doing is we're letting n go to infinity. So if we take the limit as n goes to infinity of the left-hand estimate, eventually it'll equal the limit as n goes to infinity of the right-hand estimate, which will be the exact area under the curve, which is represented by the definite integral. And you'll see that symbol that looks like an S. The integral from a to b of f of t dt is called the definite integral. So for the purposes of this class, we're going to compute integrals using either a computer or a calculator. If you go on to take Math 128, you'll learn more in-depth ways to calculate integrals by hand with all the special formulas. But for now, you should take the time to familiarize yourself with computing integrals on your calculator. You can refer to the manual that came with it, or you can Google it online, Google your specific calculator and integrals, and it'll show you how to calculate. Once it shows you how to type it into your specific device, you should try the one here, which is the integral from 1 to 4 of x squared, and you should get an answer of 21. Because now that we know how to get an exact area under a curve, we'll do more fun things with that, but you will be doing a lot of plugging into your calculator. So now would be a good time to get yourself familiar with the calculator and to try the homework from Chapter 5, Section 2.